In the last class, we learned using a rather simple example how to go about deriving a mathematical model of a physical system from the basic principles. That means, we start from the basic principles of physics that we know, and on that basis we try to derive a mathematical model of a system. And while we are doing so, we have to be very clear in our minds as to what is the objective the model is supposed to serve. If it is to study the dynamical behavior of a system, then it has to be a differential equation, otherwise it will be an algebraic relationship establishing an algebraic relationship between quantities. So, accordingly we have to proceed. But the basic thing was that we proceeded on the basis of our understanding about how various things in nature function. We just cast that understanding in the form of some mathematical relationships. Sometimes scientists start when we are doing so, when we are establishing some mathematical relationship between quantities, in the left hand side it can be how the quantity varies with time or the quantity itself in case of a algebraic relationship, but in all cases the left hand side and the right hand side must have the same dimension. That is one very important thing to keep in mind while deriving any system model. The left hand side and the right hand side must have the same dimension. Not only that, if there is an addition of two terms, both the terms should have the same dimension, and so on and so forth. Addition, subtraction, all that must have the same dimension. Now, out of the various quantities that we handle, there are a few quantities that are fundamental, in the sense that their dimension cannot be derived from the dimension of other quantities. These are, for example, the fundamental quantities. These are the mass, length, time. These three are the basic, and also temperature, which cannot be derived from something else. Mass is given the dimension of m, we normally write in capital letters. Length is given the dimension L, time is given the dimension T, and since time is there, temperature cannot be the same T, it is normally given as theta. So, these are the fundamental dimensions, and the dimension of every other thing is expressed in terms of these fundamental quantities. For example, the dimension of speed is length per unit time. So, L T inverse. So, speed is L T inverse, and so on and so forth. Momentum would be mass times the speed. So, m L T inverse. Force will be acceleration will be speed per unit time. So, L T to the power minus 2. The force will be mass into acceleration, m L T minus 2, and so on and so forth. To cut a long story short, every other quantity can be expressed in terms of these 4 fundamental quantities. And what I am insisting is that whenever we write an equation, at every stage we need to keep a check whether the left hand side and the right hand side have the same dimension or not, or if any quantity is added to another quantity. Sometimes if that quantity is complicated with various terms coming in, we need to check whether whatever it is added to, they have the same dimension. So, these are the things that we need to keep in check. Let me illustrate that. For example, if there is a pendulum oscillating, then suppose it is a pendulum of mass m suspended by a cord of length L, then we know from the fundamental theory that you have learnt in school that the time period, the period of the pendulum tau, let us call it tau, is 2 pi square root of L by G. Let us check if this equation satisfies the dimensional consistency. That is important. So, let us write here, whenever write the dimension of, then we always put that in square bracket. So, we will have to write the dimension of tau should be equal to the dimension of 2 pi times the dimension of L divided by the dimension of G square root, so to the power half. So, this is how we will express the dimensional equation. Now, the dimension of tau is the time period, therefore, it has the dimension of time. Let us write down the dimension of the right hand side first, and then let us see if that equals t. So, let me erase this first. Let us work out the dimension of the right hand side first. The dimension of 2 pi, pi is in radians, which is a ratio, and therefore, it is non-dimensional. So, this will disappear, it does not have a dimension. The dimension of L is L length, the dimension of G is an acceleration due to gravity, therefore, acceleration, and we have written that as L t to the power minus 2, this whole thing to the power half. L cancels off, t becomes t square to the power half is dimension of time. In a similar fashion, whenever we have to write an equation, then at every stage we need to check whether this is dimensionally consistent or not. Now, often in equations we come across expressions of the form sine, cosine, or let me write the whole thing, sin theta, since theta is representing time, let me do that in terms of something else, sin alpha, cos alpha, or e to the power alpha, or the ln log of alpha. So, these are transcendental expressions, and what would be the dimension of these things, both the argument of the expression as well as the whole, the result of the expression. What will be the dimension of that? In deciding that, we have to note that all these expressions, these kind of expressions, take only non-dimensional quantities as argument and return non-dimensional quantities always. And because of that, whenever we write something after a sign, that means sign of something, then we have to make sure that whatever you are taking a sinusoidal function of, that is a non-dimensional quantity. Similarly, e to the power something exponential of something, that something has to be non-dimensional quantity. Log of something, that something has to be a non-dimensional quantity, and the result of taking a log is also a non-dimensional quantity. And that is why whenever we use any of these terms, we have to always check. Just to give an example, a simple example, we often write x as a function of time is equal to some constant times sin omega t plus some phase phi, say. Now, if the phi is in radians, it is non-dimensional, but how about this? Notice that the dimension of t is t and the dimension of omega is 1 by t, because it is cycles per second. So, it is 1 by t, and therefore, the product is non-dimensional. A non-dimensional quantity added to a non-dimensional quantity is a non-dimensional quantity. Therefore, you can take a sign of that. Now, x t is a length, and therefore, it might be a length, it could be something else also, but if it is a length, then it has a dimension, and therefore, a must have the same dimension. So, x t and a must have the same dimension. Okay. So, so far so good. It is interesting to note that in many cases, even a simple dimensional analysis gives us a lot of clue regarding the relationship between quantities and allows us to derive mathematical model, a simple dimensional analysis. All that we need to do is exactly the same thing that we initially did for deriving a mathematical model. That means, first identify the phenomenon that we are trying to model, and then try to figure out what does it depend on, and that dependence we write, and in this case we write the dimension of all these quantities on which it is dependent. As earlier also, we sort of figure out which factors are relatively unimportant, which factors are more important, and put those factors in the dependence equation, and then on that basis we proceed. Let us give an example. For example, let us take an example problem. suppose I have a cannon, which shoots cannonballs at some angle, the ball will rise and then would fall. And we know that the path is a parabolic path. But suppose you do not know this, suppose you do not know the Newton's laws and you are trying to figure out the distance d, how far it will actually travel, the distance d. What will you do? You will first try to figure out what can that d depend on. Firstly, your common sense will tell that okay, I have put a mass of cannonball here and therefore, it will depend on let me write it this way, it will depend on d depends on say the mass of the ball, of the cannonball. It will of course, from common sense you figure out that it will depend on the speed, velocity with which it is ejected from the cannon. So, the u, it depends on the initial velocity u. Of course, it will depend on the angle say theta, at that angle it has been ejected, and it will depend, your common sense tells us that it will also should depend on theta. You might stop at that, but your common sense might also tell you that this distance will be different if the mass is the same, u is the same, theta is the same. It will be different dependent on whether the whole thing is being done on the surface of the earth or on the surface of the moon or on the surface of the planet Mars. So, which means that it should depend on the acceleration due to gravity. So, you then add that also and then maybe stop, and you also figure that the air friction might have a role to play, but you sort of in the initial part of the exercise of deriving a model, you say that that effect is relatively unimportant, relatively small, and therefore, in the initial phase we will ignore that. So, ignore air friction. You have to state the assumptions. And so, you write your d as a function of these things m, u, theta, g, and you do not know what kind of dependence is there. Now, the line of argument will be as follows: m is a dimensional quantity, it has a dimension m. U is a dimensional quantity, speed, and therefore, L T inverse. G is a dimensional quantity, acceleration due to gravity, acceleration, and therefore, the dimension is L T to the power minus 2. Theta, however, expressed in radians is non-dimensional. So, we understand that m, u, g are dimensional, and theta is non-dimensional. And the moment you have identified these as dimension, you know that these this cannot appear in a sinusoidal term, e to the power x term, ln term, that kind of term. These cannot appear in that, but theta can. Theta can have a transcendental function it can be argument of a transcendental function, but these cannot. Then what kind of functional form can these take? The only functional form it can take is a power. So, any dimensional quantity can take only a power. So, a power means m to the power something, u to the power something, g to the power something, these are possible, but sine, cos, log, e to the power x, exponential, all these are not possible. And therefore, we write the d as m to the power some number to the power is power, u to the power beta, g to the power another thing, say delta. Now, theta will can take any arbitrary function, and therefore, we do not know that function. So, we have to write that as some function of theta. We do not know what this function is, but we cannot simply state that it can only take a to the power kind of functional form. No, it can take any functional form, because it is non-dimensional. And in addition, there can be some proportionality constant upfront. So, that becomes our initial model. Now, let us put the dimensions, then it becomes the dimensional equation becomes the dimension of D will be equal to dimension of k times the dimension of m to the power alpha times the dimension of u to the power beta times the dimension of g to the power delta. Now, h of theta is not a dimensional quantity, and therefore, there should be no dimension here. And you might say that I have chosen the k to be a non-dimensional quantity also, because it is not necessary that k should have a dimension. Therefore, we can ignore that. So, this becomes basically the dimensional equation. Now, if I now write the dimensions, m's dimension is capital M to the power alpha, u is L T inverse whole to the power beta, and this is L T minus 2 whole to the power delta. Okay. And if you now expand it, you get m to the power alpha, L to the power beta times L to the power delta. So, L to the power beta plus delta, and here t to the power minus 1 and t to the power minus 2, or this will be t to the power minus beta and t to the power minus 2 delta. Therefore, t to the power minus beta minus 2 delta. And in the left hand side, the dimension is d, which is L. Now, notice the left hand side and the right hand side have to have the same dimension. That immediately tells us that m to the power alpha has to disappear, because m, there is no m in the left hand side. So, alpha, the only possible value is alpha has to be equal to 0. Now, here the power of L is 1, the power of L here is beta plus delta. Therefore, beta plus delta is equal to 1, and from here, since there is no t in the left hand side, therefore, minus beta minus 2 delta should be equal to 0. And you can solve these two equations. This gives beta is equal to 1 minus delta, and then you put it here, it becomes minus 1 minus delta minus 2 delta equal to 0. Therefore, minus 1 plus delta minus 2 delta. So, this is minus delta equal to 0. So, delta is equal to minus 1. Put that here, delta is equal to minus 1, it becomes 2, beta is equal to 2. Okay. Therefore, we have actually obtained the equation d. We can now write d is equal to some constant, which is a non-dimensional constant, times let us first write the term that was there, so that we do not forget it, h theta. And now, m to the power alpha, alpha is 0, and therefore, this disappears. U to the power beta, beta is 2. So, u square, g to the power delta, delta is minus 1. So, by g. So, that then will be the relationship that you have obtained. It is clear that we do not yet know the functional relationship, but one noticeable, very important noticeable thing is that using simply dimension analysis, we have come to the conclusion that the distance to which the cannonball will go does not depend on the mass of the cannonball. That was not following from common sense. When we did not know the Newton's equation, we did not know that it will not depend on the mass of the cannonball, but simple dimension analysis allows us to come to that conclusion. And now, once we know this particular term, and you have g as a something constant on the surface of the earth, then you know that it is d is proportional to u square, and we do not know this functional form. So, how do we do that? Now, we have to perform very directed experiments in order to derive this functional form. How do we do that? We now know from Newton's theory that h of theta is actually sin 2 theta, and at theta is equal to 45 degree, it maximizes, and for lower values of theta and for higher values of theta, the d will be smaller. Now, when we were doing the curve fitting, we actually said that from the data, we can either fit into a linear curve or a power law or an exponential curve. But beyond that, we said that it would be difficult. So, in this case, either from theory you sort of you have to guess the kind of functional form and then you can test, but with no prior idea regarding what kind of functional form it should fit, because it will be a curve like this, and therefore, what kind of functional form it will fit you never know, and that is why from the data you have to obtain, since you are trying to find out some kind of a functional form, you have to plot the kind of data in this form. Theta here and h of theta here. For each theta, you do the experiment at each theta keeping u constant, because this is the dependence you are trying to figure out. Keep u constant, u square by g becomes a constant. The distances are measured, and these presently you assume k to be just a proportionality. So, do not bother about it. So, d times g by u square is something that is calculated, the distance is calculated, and that is should be equal to the h theta. So, this is what is plotted, and if you plot it, you get something like this, you should get something like this, and here is our 45 degrees. Now, you cannot fit a curve like this into either the power law or exponential or a linear curve. So, in order to get the functional form, you have to guess what it could be. A curve like this could fit a parabola, could fit a sinusoid, and you might, if you have some idea that it might be a sinusoid, then you fit a sinusoid, and then if it is likely to fit a parabola, then you fit a parabola. Okay. In this case, it would fit a sinusoidal graph.